All right, section 1.4, relations and functions. So we need to be able to identify the domain and range. So those are a couple keywords that we're going to be doing today. And then also determine whether a relation is a function or not. So, you have relations, which are just some relationship between two things. But then whether or not it turns out to be a function, there's a few different tests we can do. So that's where we're headed. Let's jump right into this. So a relation, here's the definition, is a pairing of input values and output values. So basically that's all it is. You put something in and then it maps to something else. This can be expressed as a set of ordered pairs or as a mapping diagram, and we'll do this down here in a minute in example 1 and 2. The set of input values is called the domain. Right? So the domain is the input values. And then the set of the output values is what is known as the range. Now range has other meanings, like in statistics, the range is, the difference between the highest piece of data and the lowest piece of data. So range can mean different things in different applications, but here you want to tie it in with the output. And it says, consider the average weight of male children in the table below. So we're looking at 1, 2, 3, and 4-year-olds, and then the average weight of those kids. And it was kind of an interval, but I just kind of picked the median or the middle number for each one. So it says, number 1, write as a set of ordered pairs. So our inputs are the age. So when you put an input of 1, you get a weight of 19. And then 2 pairs up with 29, 3 pairs up with 32, and 4 would pair up with 37. And that could be on a graph. You could very easily could put this on a graph. So if you wanted to, you would put the age, and typically time or age, things like that go on the bottom. So you'd have 1, 2, 3, 4. And then we're going up to 40. So I'll just go 40, go 20, put in a couple in between spots. And we actually could graph this relation. So we could have a set of ordered pairs, but then we could also map it out and do like 1 goes to 19, 2 goes to 29, and 3 goes to 32, and then 4 up to about 37. So we could see that this is not a linear relationship. What we cannot do is we cannot connect the dots right now, because these are the only dots that we have information on. We don't know about, at 1.1 or 1.2 or 1.3. So be careful whenever you're doing this section where you're just mapping out relations. Don't connect the dots. So we could also show this in mapping notation. So let me just kind of show you what that is. I'm going to come down, and mapping notation looks something like this, where we have I'll put D for domain and R for our range. And basically you put all of the elements that are in the domain, like 1, 2, 3, and 4, you write those over here. And then you put your elements that are in the range, 19, 29, 32, and 37. And the order doesn't really matter, because in a mapping situation, you kind of draw arrows that show which number maps to which number. In this case, they just all go straight across, but sometimes you may have like 2 different ages that map to the same number. And I'm sure if we'd extended this chart out, you might be able to get to something where it says, hey, a 40-year-old male and then a 41-year-old male, and maybe they would both be like 192 pounds. All right. So maybe if that chart got extended, it would look like that. So when you map it, occasionally you'll have 2 elements or more in the domain. And you can also think of this as like the domain or the X values. You may have a big old set over here. Well, you may have 2 different people map to the same number. Like that's totally fine. That can happen like that. Down here it says the domain, and it kind of has it in colon. So we're going to use set notation. So you kind of have this squiggly brace. So the domain, we're going to put all of the x values or all the inputs. So 1, 2, 3, and 4. So that would be the domain. And then the range, we're going to put in the y values. So nothing today really too, like you're not really calculating anything. Today's just kind of more vocabulary and understanding who's the domain, who's the range. And this will tie a lot more into graphing later on. But right now we're just kind of thinking about objects and thinking about values in a table. Harvard tuition. So I looked this up because I was having a conversation with somebody about like how college has gotten so crazy. So I kind of went by 15-year intervals. And in 1960, Harvard's tuition, that's not including room and board, so no dorms or meals, but just the tuition, was only $1,520. And even back in 1990, I graduated in 91, the price was only $13,000. And now, well, the last one I saw was 2020, it's almost up to $48,000. So pretty crazy. It's just exponentially how college has grown. So you hear old timers back in the day be like, yeah, I worked and paid my way through college. Well, when you look at the salaries back then compared to what college cost, like it's impossible nowadays. The salaries just have not went up the same amount that the tuition has went up. So it's really getting harder and harder for kids to pay for school. So give the domain and range for the relation between the year and the tuition rate. So the domain, you just put D, colon, and then I put in the years, 1960, 1975, 1990, 2005. So these are all the inputs. Domain, remember, is what goes in. And then the outputs are the range. And these are the tuition numbers. I'm not going to put commas in here just to kind of save time. But I'm just copying down. Think of them as x values and y values. In the next lesson, we'll get into dependent and independent variables. But we're just getting our feet wet. So domain and range. All right, a function is a special type of relation. So if you kind of think about like a Venn diagram, and you think about, let's say all of this stuff in here are relations. Well, there's a subset that are called functions. So they're a special type of relation where every element, everything, every object in the domain is mapped to exactly and only one element in the range. So, every x is being mapped to its own unique y value. So basically, if you're thinking about like a set of ordered pairs, this would be an example of a function. So this is a function. And I'm going to pick some ordered pairs. So 1 to 2, 2 to 4, 3, let's say to -1, and 4 goes to, we'll just say 5. All right? So that's an example of a function because when I look at it, every single element in the domain is mapped to exactly one in the range. So, if I kind of look at it like our example from before, and I put if I put all of our x values, our domains, 1, 2, 3, and 4, they all go to exclusively their own person over here in the range. So over here I have a -1, I have a 2, I have a 4, and I have a 5. And when you connect them up, 1 goes to 2, 2 goes to 4, 3 goes to -1, and 4 goes to 5. Everybody has their own unique pair. Now, occasionally you'll get something kind of weird, and this would be something that's not a function. And I'm not going to write out all the ordered pairs, but I'm going to kind of show you on a map. So if this is the domain and this is the range, or you can think of it as x and y's. Let's say I have a 1, 2, and 3. And let's say over here I have -1, -4, 7, and 8. And maybe you have something like this going on. All right. Well, that's not a function. And the reason that it's not a function, like where the problem is right here. Because we violate the definition, because it said that every element in the domain is mapped to exactly only one element. Well, we have this problem here where 1 mapped to -4, but then it says, oh, I'm going to also come down here and map to 8. You know, it's kind of like, almost think of it like prom. You know, like this person number 1 just basically went and asked 2 different people if they want to go to prom, which is probably not a good idea, because what if they both say yes? Now you're in a bind, now you're in a pickle. So, you know, that one can't map to 2 different people. Now, it's totally okay, and we're going to see this in an example before, where you might have 2 elements in the domain mapped to one in the same range. So for instance, you could have this happen, where you have, say, 1, 2, and 3, and you have a 4 and a 5, and maybe you have that, and you have that. Well, yes, this is a function, because 1 mapped to his unique person, 2 mapped to somebody, and 3 mapped to somebody. None of those people ever mapped to 2 different places. You know, in the prom example, I guess we kind of hold up here because, hey, this isn't really a problem. Number 5 just happened to get asked by 2 different people. There's really nothing wrong with that. If number 2 and number 3 didn't know each other, and they didn't know that somebody else was going to ask 5, that'd be no big deal. They both just ask 5, and 5 decides who they want to go with. But for a person in the domain to ask 2 different y's, that's kind of shady. So this one would be yes, this is a function. All right, hopefully it'll clear up when we do some examples. So number 4, determine whether each relation is a function. So what I'm doing is I'm going to check all the x values. So 1 mapped to 4. And I look and see, did 1 map to anybody else? Nope. So 1, you're okay. -2 maps to 7. I don't see any other -2s, so we're good. 3 goes to 6. There's no other 3s. So 4. So basically, there were no x's that repeated. So as long as I didn't get a repeat there, it was impossible for an x to map to 2 different y's. So this one is definitely a yes. This is a function. Everything is cool. There are no problems. You know, if I would have saw that 1 mapped to somebody else later on, then I'd be like, hey, 1's cheating. It's not a function. So basically, you can kind of think of it as, this is how I like to think of it, is the x's can't cheat. All right, x's can't cheat. Okay, the y's can kind of do what they want. The y's are allowed to, but the x's can't. So number 5, is it a function if you map from the number of items in a grocery cart to the total cost in the cart? So think about if I was in the grocery store and I was going to map the number of items in a cart. So notice how it said from to. So we're going from the items in the cart to the cost. So I have the number of items to the cost. Well, I don't think this would be a function, because I do think it's possible if we're standing in that grocery store and they're coming up to the line, you may have a cart with 5 items mapped to, $8, but then you may have another cart with 5 items only mapped to like $2.50. So I don't think if you know the items in a cart, you're going to get one unique cost of those items. It's going to vary. So this one would be no. It's not a function. Now, how about if you know somebody's last name, could you identify their security number? Well, again, I think that one is no. Because for instance, you could have, if I just said, hey, Jones, that's what you're given. You know the last name of Jones. There's going to be millions of Social Security numbers. Okay, when you go across the country, there's millions of Joneses. There's going to be a ton of different numbers. So just because I know the last name of Jones, it's not going to map to a unique Social Security number. Now it says, how about from a Social Security number to a last name? I think this is a yes. Because if you say, hey, you're given a Social Security number, and I'm just making one up, 341109999. If I'm given that is going to map directly to one unique person who has a last name. I guess you could get into like, well, what if they changed it? That kind of stuff. But if you're given a Social Security number, that will lead you to exactly one person. But the other's not quite true. All right, now with graphs, there's kind of a special test that we can do. When the relation is a graph, you can determine whether or not it's a function by using a vertical line test. So I'm going to just kind of explain really quickly how this works. So if I have the graph here, this red squiggly line, almost like a sine or a cosine curve, if you do a vertical line, you're never going to touch two spots on the graph. So this one that says function, you never touch two spots. However, the equation here on the right, if you look at that dotted blue line coming down, there's a problem. And the problem occurs right there and right there. I had a vertical line touch my graph in two places. So let's just pretend that this was at like 1, 2. Let's pretend that that's at 3. If I were to graph that out, I would have a situation where 3 went to some positive number. Let's say maybe that was at 3, 3. But then I also had a situation down here where 3 went to a negative number, negative 3. So if you think about a map, we just had an issue where we had an input go to two different outputs. And when that happens, it's not a function. So it's really easy with graphs. You can just do a vertical line test. You don't really have to analyze all the pairs. So it says use a vertical line test to determine whether each relation is a function. If not, identify the 2 points where the vertical line would pass through. So let's just kind of go through these. Looking at this first pair, right away I see a problem. I see an issue right here where I just hit 2 dots with a vertical line. And that occurred at x equals 5. So I think that was where our problem was. We had a problem like at 5, 3, which would represent this dot. And then, I don't know, that one we have to kind of guess at, maybe 5.27 or 0.27. So there was our issue. There were our 2 points where we had a violation. We had one x that mapped to 2 y's. Well, over here on the next chart, I really don't see anywhere, if we keep going and going and going, I don't see anywhere where we're going to have one x touch 2 different places. So I think this one is going to be yes, it is a function. This one over here was no. I think this one in the bottom left, yes, it is a function. I don't see any issues, nowhere where there's one x that goes to 2 y's. I do see a problem right here with a vertical line test because it looks like 1 mapped to positive 2, but then later on 1 mapped to negative 2. So that's an issue. So this one is going to be not a function. So it's nice when you don't have to sift through all the ordered pairs and you can just do a vertical line test for a graphing relation. All right, then we get into the practice. So I'm going to let you battle with that, and then we can take questions in class. Hopefully this helps you out. If you have any questions on the notes, talk to me in class tomorrow. See you.